Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman. I'm the Marketing Director here at the Academy. Here with us today, we have Dr. David Vicari. Dr. Vicari is a professor of environmental engineering at Stevens Institute of Technology. Today, he will be talking about modeling complex environmental data without a black box. Dr. Vicari is a board-certified environmental engineer, and he's actually the Academy's president-elect, so he will be taking office in January of 2023. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, you'll be able to type your question into the attendee chat panel on the left-hand side of your screen. Okay, let's get started. Welcome, Dr. Vicari. Thank you for joining us today, and we're ready when you are.
Okay, Marissa, thank you very much for the introduction. And thanks everybody for joining in with us today. I'm going to be describing a statistical regression approach to looking at data. So it's a little bit on the technical side, but I would claim that the environmental field as a whole needs to embrace what people are calling artificial intelligence, and this statistical regression approach that I'm going to describe, while it's a more traditional type of modeling approach than the newer artificial intelligence technologies, it has similar capabilities. So that's what I would like to describe. I was led into this myself. Here you see a picture of me. That's not a sewer pipe I'm in. That's called a moon gate in Beijing. And down on the lower right is a final clarifier from a wastewater treatment plant. And that was what I started being interested in, was trying to predict the performance of wastewater treatment plants. And of course, we have sophisticated mechanistic models to do that using Monod equations based on fundamental principles and so on. And I was dealing in those types of models, and then kind of ran up against a limit in trying to predict the overall performance of the plant, because there are other parameters that didn't fit into the models, turbidity and composition, divalent ion composition that affected sedimentation in the clarifier in ways that could not be predicted using our fundamental physical, chemical, and biological theories. So this led me to empirical or statistical type of modeling. So let me outline the talk. So I'm going to start kind of simple, assume that there's some people that this is really very new for, and kind of move quickly into the topic itself. And I'm going to compare it to one of the dominant artificial intelligence approaches, which is the artificial neural network. Then I'll start talking about the specific approach that I'm describing here, the multivariate polynomial regression, or MPR. And then I'm going to show a piece of software that I developed that is freely available on the web. And I'll show some of its features. And this will illustrate some of the capabilities that the statistical approach has over neural networks, uh, uh, even though you have similar capabilities. And then I'll give several examples, right? So here's the overall problem. You've got some kind of system, that blue box in the middle there. And there are what we call the independent variables. Those are the causations, the causative variables. And if you put them into the system, they produce some kind of result, the dependent variable. Okay, many examples. This is everywhere you look. For example, in water quality, if you want to predict how much algae is growing, which we measure as chlorophyll A, what does that depend on? Temperature, total phosphorus loading, water temperature, hydrodynamic parameters, meteorological parameters, wind and sunshine and so on. Other water quality indices, and I'll be doing an example on this specifically, looking at macrophyte indices, will depend on possibly many physical and chemical parameters, nutrient conditions, oxygen, BOD, physical chemical types of parameters. So these are input-output type of things where you're trying to take these inputs and predict something directly. Time is not involved there. It's kind of fixed. There's also the time series type situation. I'm just going to mention briefly, but not give examples of this. But for example, if you want to predict the river discharge, you want to know how much precipitation there's been recently in the past 1, 2, 3 hours, or even days before. So the discharge at this moment depends on that kind of history. And using that history as inputs, that gives you what's known as a time series model. So how do we make the connection between those multiple inputs and the output if we don't have a theoretical relationship for doing that? One of the best known and most commonly used is a linear technique called multilinear regression. So I'm going to start there and go on then to talk about then the nonlinear approaches, which can take into account what I call complex behaviors. And I'm going to define what I mean by complex behavior in a moment. But I'm going to compare the two nonlinear approaches, the artificial neural networks and the multivariate polynomial regression. So everyone's heard about artificial neural networks. Let me talk about that first. It's often described as a black box, and similar to what I was describing before, it takes multiple inputs. Let me get my pointer here going. So here's our multiple inputs, goes into a system and produces some kind of result. And if you collect a lot of data, you can, in the regression sense, you fit the model to the data. In the neural network sense, they call it training the network, which really is also a fitting process. What's going on inside that black box is you take the inputs and you put it into a node, which then executes what's called kind of a squashing function. It's just a sigmoid relationship. It takes the inputs, sums them up. It takes a weighted sum, puts it through that squashing function, and passes it on. So you see each node then produces an output that goes to the next layer of nodes, and that takes a weighted sum, and each of these little small black dots is a weighting coefficient. And that's the adjustable parameter in the neural network. And training, what they call training the neural network, consists of just incrementally adjusting these values of these multipliers here until you get a good fit. But the result is still going to be a black box. I mean, the advantages are you can get very accurate descriptions of this complex behavior that I described that. And you can handle very high dimensional problems like image analysis and so on, very relatively easy. Problem is, it is complex. It's hard to analyze, and I'm going to show you how analysis that I can do with MPR is pretty straightforward. Big one that I like to emphasize is the difficulty in communicating your results. When you see in the literature that people have applied neural networks to a problem, what they typically do is they say, here's what I did, here's how well it worked, and now you go do it. They don't actually publish the model, whereas our mechanistic models and our statistical models, you can publish them usually as an equation with coefficients and statistics about that. Typically, it's not done with neural networks. Another problem is that it's susceptible to overfitting. That's called memorizing the noise. And that's because there are so many coefficients being thrown at the problem. And basically, it's hidden behavior. It's a black box. Right? So let me talk about regression. And just as a reminder, I'll start with simple linear regression. Y equals ax plus b, right? You try to fit a straight line through the points, and you get these errors. Right? You cannot always make your line go through every point. So your problem then is really to find the slope and intercept that minimizes the sum of we use the sum of the squares of those errors. Right? And we're going to compare that to the line with no slope. In other words, the line that does not depend on your x value. And that line of best fit turns out to be the arithmetic mean, the average. And if we calculate the errors in the same way and take the sum of those squares, we get what's known as the total sum of squares. And the sum of squares of the errors generally is going to be between 0, which means no error, the line goes right through everything, or it's going to be equal to the total sum of squares, which means the x value doesn't give you any predictive power. So the worst case is the SSE equals the total sum of squares. X provides no predictive power. The best case is sum of squares of error is 0. So that suggests then a parameter that goes from 0 to 1, which is the well-known r squared, and can be computationally calculated with the sum of squares of errors and total sum of squares. So that's going to be between 0 and 1. And it's roughly how much of the variance in your dependent variable you've explained with your model. Now let me extend this to the multivariable case. As before, we have our y equals intercept plus slope times x, where there's a single value of x. But what if you have multiple causes, multiple inputs affecting your result? Well, we can just add additional linear terms, a separate slope factor times the second variable, the third slope factor times the third variable, and so on. Okay. One of the problems is, especially if you have a lot of data, say you have a lot of water quality data and you want to predict a biotic index. Some of them may be affecting the biotic index, some of them might not be. But it's a curious property when you do multilinear regression, is that if you add more variables, the r squared always goes up. So when do you stop? If you put in too many variables, this also runs the danger of overfitting. So, and also, how do you know if the r squared is how good is good enough? Okay. So what we need are goodness of fit statistics that penalize too much complexity in the model. Now I'm going to throw out some. This is probably going to be the more complex slide that I'll develop things through. Can't avoid throwing out some equations here. I tried to keep it to a minimum, but so there's the r squared as I've already defined it. We want to penalize that somehow, and the way we'll do it is by taking into account the degrees of freedom, df, which is the number of data points you have, that rows in your Excel spreadsheet, say, minus how many parameters, that is, how many coefficients there are in your model. Right, that's the degrees of freedom. And I also define this thing called the sum of squares of the regression, which is the difference between the TSS and SSE. Anyway, with these additional parameters, we can calculate a kind of a replacement for the total sum of squares, which we call total mean squares. And I just divide by the number of data minus 1. So the more data I have, the more accurately I know this. And you might recognize this is simply the variance of the data. The error I divide by the degrees of freedom. And this turns out to also be the variance of your errors. And the degrees of freedom, of course, the more complex your model is, the smaller that gets. So that's where the penalty comes in. And we do a similar thing with mean square of the regression. Anyway, I'm going to take this r squared, and instead of SSE, I'm going to use MSE. And instead of TSS, I'll use TMS. So I'm using those adjusted parameters that take into account complexity, and I get what's known as the adjusted R squared. And this is actually a better value to use, and this does not always increase, okay? And incidentally, we can calculate a related parameter called the F statistic, which is the ratio of mean square of the regression to the mean square of the error. And this is basically a signal to noise ratio. And it has an advantage that has statistical properties that enable us to calculate its probability of having a larger value. So if we can calculate, there's an Excel function for this that'll give us the probability of a larger value of f occurring by chance. And if that probability is too high, it means our model is not statistically significant. Okay. Since f and r adjusted R squared are all based on the same variables, there's a relationship between the two. So that means with the adjusted R squared, we can turn it back into the f and get that probability. We can find a probability associated with the adjusted R squared. So that gives us the meaning about how much R squared is good enough. Okay. So am I on the wrong slide? No. Okay, this is right. So all these are based on just these four parameters: the total sum of squares of the error, and the number of data, number of parameters. Okay. I want to make sure, I want to know if someone can confirm that I'm seeing some glitches on my screen here. What you should be seeing now is a slide. The title says How to Make Models Concise, Stepwise Regression for Multilinear Regression. Now, I don't know if Marissa is still there. She can confirm.
Yes, I see stepwise regression for MLR.
Good. Okay. All right. I've seen some ambiguous things on my screens because I'm using two screens here. So there are a variety of techniques for making sure you don't have too many terms in the model. One is to start with all those possible terms that could be in there, add them one by one, and check the things like the F statistic and other parameters. Pick the best one, put it in the model. If there's anything previously added to the model that is not significant, you take it out, and then you repeat until you cannot improve the model by either adding or removing a single term, and then you're done. All right. So I'm going to jump out now and go to the software that I'm talking about. And this is, as I mentioned, this is free online software. It doesn't even require registration. So I'm going to stop the presentation briefly and go to the software. I've already preloaded some data in here, and you see the name of the website here. It's tailorfit-rsa.com. And if I mouse down to the bottom here, you see my data sets. So I have rows 1 through, this shows the first 10 rows. There are about 200 here. And this particular data set is on the strength of concrete. And you see one column has the strength of concrete here. And that depends on some inputs: the cement content, the slag, ash, water content, and other ingredients, plus how many days it's been aged. And you get a certain measured compressive strength. Those of you who are civil engineers know what I mean here. And we'd like to predict the strength based on these other 8 parameters. Right? Now, TaylorFit lets you do this very easily. The grade part, by the way, is just statistics about the columns. But over here, it shows the multilinear individual regression terms. And it shows something called a t statistic, which is a parameter that tells me what I'm going to be most interested in is the probability of the t. I want this to be less than 5% or 0.05. All right. And I'm also going to add in, I'm going to look at the same time, adjusted R squared. So you see I've added that column here. And I want you to notice that down here in the data, I have a second data called cross data. This is for something called cross validation that I'm going to talk about later. I'm going to actually use simultaneous. I'm going to look at those 2 data sets. I want to have a significant t, and also my adjusted R squared has to be improved over the old one. Over here, it shows you the current model. Current model has only a constant, which has a value of 39.5. That's basically the average of the data. There are no terms using x values in the model yet. This table shows all various statistics, including my R-squared and my adjusted R-squared, which is 0 now because I haven't added any terms to the model. So I will go over here now, and I'm going to start with the most significant single term is to put in the amount of cement. Just click on that. It shows up here, and now I have two terms, the intercept and a single slope term, and my adjusted R-squared is about 0.21, right? But I'm going to go on and continue adding until I don't get any very simple thing. I just want to do it until none of these terms show two green cells. So the green indicates that it's an improvement. So coarse aggregate and fine aggregate don't seem to matter, so I don't add them. And here's my best model. Right? My adjusted R squared is now about 56%, big improvement. I could stop here. I can download the code and copy this into a program or an Excel file or whatever, and I'm done. Okay, so that's a multilinear regression model. Going on, go back to the presentation. Now, what's the problem with this? Problem is that it's linear. So here's my linear regression case in the XY type situation. What if I have this kind of situation? Both of these data sets have the same mean standard deviation in R squared, but clearly case 2 here is not a good model. So this is called model specification bias. The same thing could happen with, I have 8 inputs for that concrete example, but I can't look at a graph in really 9 dimensions. So I need a different way to test for this. But let me show you what's going on in 3 dimensions. Well, let's just use 2 dimensions at a time. The XY case. So multilinear regression is, for example, Z depends on X and Y. So here's my multilinear model. I'm going to be interested in how Z changes if I change X. So that's the slope of the model, which is just A1. And mathematically, that's the derivative of Z with respect to X, right? I got to go into a little calculus here. I'm sorry. So it's a constant. It's A1. But what if your data does this? Okay, that the slope with respect to X changes if you change the value of Y. So I get 2 different lines with different slopes. Turns out there's a pretty standard way to do this, and just add a different term into the model, X times Y. And this is called an interaction term. And with 8 variables, you can get a lot of interactions going on, and it could be more than a 2-way interaction too. This is where we start getting into what I call complexity. All right? But if I take the derivative of this term added in, I add this term here, and now my derivative with respect to X depends on Y. And I am looking at what's going on. Right? What if your data does this, though? Now we got that misspecification problem. We're fitting straight lines to data that don't conform to straight lines. The data should be telling us the form of the model, not us specifying the model in advance unless we check. So how can we handle that? Well, we can put in multivariate polynomial terms like x squared y cubed, or even x times y to the minus 1. That means x divided by y. Now, you know, ratios are often found in physical situations. If we don't check for the ratio of our variables, but that's a meaningful thing, we're running the risk of misspecifying. Right? It's a polynomial. It looks a little more complicated, but calculating the derivative is pretty simple. So we can do that. Right? If there are nonlinear relationships like these in your data, and you don't consider them, you're going to have a biased model. Let me show you another way of looking at it. The multilinear case, like Z is just x plus y. It's the in 3 dimensions, it's a surface, a plane surface. It's a flat plane. No matter how you cut it, you get a straight line. The interaction term gives you a saddle shape. Again, if your data exhibit this type of property and you don't account for it, you're misspecifying. But other polynomial type relationships show other shapes. This is one I call the slippery slope. Two corners, adjacent corners, are turned down, the other two are turned up. Right? Totally different from those other three shapes. And again, your data might have this behavior, maybe not. Right? X squared, Y squared, I call that the bucket, where it's sort of like a blanket being picked up on the four corners. Totally different. Right? And others, X, Y cubed, I just had to come up with a name, so I call it the raptor. Right? The ratios, that's kind of a twisted sheet. And saturation, also a phenomenon, is very common. It's a different type of twisted sheet. Okay, so we want to look at these polynomial terms. Right? Now, we can start throwing in polynomial terms. Here's, if I have three independent variables, this is the multilinear model right here. And I can start putting in the possible interactions and the possible polynomials, limiting myself to second order. I get a lot of possible terms, about 27. But here again, maybe not all of these are important. We need a way to limit the model complexity. And the technique I use here is the one I just described before, the stepwise regression, where I add and remove terms one at a time until I can't improve the model by either adding another one or removing one. Right? So TaylorFit, that's the website, lets you account for the same kind of complexity, and this is similar to the complexity that neural networks will account for. We get similar accuracy, but we get transparency, transportability. You can write down that equation. It's unbiased. It's tractable. It means you can do. You can plug it into your programs and your spreadsheets to do calculations, and it's more resistant to overfitting than neural networks. Right? So there are a couple of other things. I mentioned cross validation. That essentially says you look at two data sets at the same time, and you use different statistics with the two, and you want to satisfy both at the same time. And you use one for fitting and one for testing. And that further ensures that you don't put in unnecessary parameters. All right? And you should have a third data set. You don't always have enough data for this, but when possible, the gold standard is final validation. Only when you're all done, you test to see how well it works. All right. So going back now to TaylorFit here, the only thing I want to change is now I'm going to start by, see where it says max multiplicands on the right side over here. Right now it's looking at one at a time. If I increase this to 2 and come out of here, now it's looking at the two-way interactions, and it's sorted them by which ones have the best t-statistics. But I'm only going to pick it if it also improves my coarse correlation here. So I'm going to add in the product of plasticizer and coarse aggregate. So I click on this, it goes in the model. You can see it over here on the left side. And I got a bit of an increase in my adjusted R squared. Looks like my next best one is the product of cement times age. In it goes. And I do this repeatedly until, again, I can no longer improve my model by fixing both. And I'm there already. But I want to put in polynomial terms. So I'm going to turn on my exponent 2. And I'm also going to add in exponent of -1, which will allow me to take ratios. I'll recalculate, come out. And now we see we have a lot of choices, like 1 over the product of fine aggregate and age. So it's not a ratio. But just to show you an example of a ratio, I will. So here's coarse aggregate squared times age squared. I'll put that in. Now here's an interesting thing. In the stepwise procedure, you see the red cell over here? Its probability is much greater than 0.05, so I'm going to take it back out. Sometimes after you add something, a previous term becomes not significant. Then I go back over to the right to look at these terms here and look for, here's a ratio. course aggregate times age to the minus 1. That's the ratio of course aggregate age into the model it goes. I'm going to stop here, even though I could keep going. My adjusted R squared is up around 81%. And even for the course validation, if I was going to stop completely here and not go any further, only then do I look at the validation, and I've got an R squared on my totally independent data set of 47%. Right. I'll go back to the presentation here. And show you some other tricks that we can do. And these are things that are built into tailor fit, and some of these are things that are hard to do in something like neural networks. The first thing I want to mention is this is not a hard thing to do in any kind of modeling approach. What you often see people do, and I just want to caution you about this is an important lesson. You often see people create a model, and then to show you how good the model is, they plot the predicted value from their model versus the observed value. Should you do that? Never. Never, never. Okay. Here's what happens. Here's the plot of this y hat is the predicted value versus y is the observed value. Okay. When you do that, because your actual values are on the x-axis, the actual values contain the error. So you're distributing your error horizontally around the line. As a result, you see what happens here? It looks like you're under-predicting your high values and over-predicting your low values. And I've seen this actually in practice. I saw this in a consultant was doing phosphorus modeling for the state of New Jersey, and they did this kind of plot of their predicted versus observed, and people were saying, oh, it's not a good fit, right? If they had simply reversed the axis and plotted observed versus predicted, now you're distributing your errors vertically around your prediction line, and visibly you don't see any error. So just a caution to you, in any kind of modeling that you do, put the predicted on the x-axis. And even better is just plot the errors versus the predicted values, and don't even plot the observed values. Basically, this is called a residuals plot, so we're plotting only the errors or the residuals left over. It should appear random and not exhibit trends. And you saw there was a little graph in tailor fit. While you're doing the fitting, it shows you this plot, basically the error versus the prediction, continuously as you go. Another way to look at these errors is to look at their histogram, their cumulative frequency distribution, or to see if they're normally distributed, what's called the QQ plot. Right? Tailor fit will generate all of these for you. Another thing you want to do, I talked about the sensitivity, how you analyze a model. So let's look at several different analysis tools, sensitivity, and then leading to confidence intervals. Now with nonlinear sensitivity, it's not a constant anymore. So how do we represent it? It's a distribution. It's going to be different for every data point. So we calculate it every data point, and we can do things like calculate its mean and standard deviation. I like to use root mean square, the RMS value. We can look at its histogram or its cumulative frequency distribution. Right? Here's another problem with sensitivity. Depends on what units you use. So the number doesn't have quite the utility. So for example, this is a different regression. I plotted the miles per gallons that cars get based on how heavy the car is. And I get a sensitivity of negative 0.0074. That means I get, for every pound of increase of weight, the MPG goes down by 0.0074. Of course, if I do it in kilograms, I'm going to get a different slope factor, right? And so that's fine. You just have to recognize the units. But then how do I compare the effect of the sensitivity of miles per gallon to weight to miles per gallon to the horsepower of the car, for example, right? Not only do they have different units, they have different meanings. You can't directly compare them. So this leads me to a different type of sensitivity where I normalize the sensitivity by the standard error of the variables involved. I won't talk about the equation much here. So I just want to point out, you get a dimensionless sensitivity. And with this, you can compare the importance ratio of weight to the importance ratio for horsepower, for example, in a car. And then you can and interpret them. It's how much the change in your independent variable changes your dependent variable relative to their spreads. So as an example, and this is one of the environmental data sets I talked about. I'll show more about this later. This shows a model that I came up with, the sensitivity distribution as importance ratio of 5 different variables. So this is electrical conductivity, nitrite concentration, BOD5, and organic nitrogen. And you'll see, for example, that I believe this is nitrite has both negative and positive sensitivity, depending on the situation. It's complex, right? How many times have you heard if someone asks an expert to say, well, what is the effect of this on that? And they say, well, it's complex. This is what it means to be complex. You know, there are multiple nonlinear interactions going on. You can't just show it in a single XY graph. Another thing that you want to look at is when you make a prediction, we get a number, but numbers have distributions. We shouldn't treat them as a single number. We should understand them to mean there's this plus or minus around it. So we understand that as the confidence interval. There's also something similar called the prediction interval. So the confidence interval is the thing where most people are somewhat familiar with. Indicates the expected spread of the prediction. So if I predict that the miles per gallon of a car is going to be 20, and at 90, I can come up with a so-called 95% confidence level, saying that 95% of the time it's going to be plus 20 plus or minus whatever, 2 miles per gallon. Okay. There's something else that contradictorily is called a prediction interval, and takes into account the added noise of the measurement. So the confidence interval is the range for the prediction. The prediction interval, ironically, is the range of your observations, which include the noise in the data. So it's the observed value plus or minus the prediction interval. I'll give a specific example in a minute. And in fact, let me go now into several examples of environmental data sets. Okay. So I'm going to do these 4 examples kind of quickly here. The first is a paper that I published with some colleagues that looked at macrophyte indices. The macrophyte index for rivers, the MIR, the nutrient index, RMNI, the macrophyte biological index, IBMR, and also several so-called diversity indices. If you've had any, if you've learned some ecology, you know what we mean by a diversity index. There's a Simpson index and a species richness. And how do these things depend on physical chemical parameters? Well, here we see it. So IBMR depends on, interesting term here, it's the product of nitrite and 5-day BOD divided by the total phosphorus, plus inverse product of total phosphorus and organic nitrogen, and so on, all these different terms. These look complex, but now people will say, well, what do these mean? What do these terms mean? And I will say, you can't always attribute a meaning to an individual term. Right? If you look at a quadratic equation, you don't ask what's the meaning of the quadratic term. You just say it just contributes to the overall shape of the response curve in n-dimensional space, which we can't visualize. But the NPR regression approach can capture that shape for you here. Right? So what we can do is we can take that model. So this is the IBMR model here, for example, and you see it has 1, 2, 3, 4, 5 terms plus an intercept term, and we can plot it in 2 dimensions if we hold all but 2 of the variables constant. So here's IBMR versus one of the more important variables, which is the organic nitrogen, and we did it at different levels of the HMS, which is called the River Hydromorphological Index. And you see that kind of nonlinear behavior that has this kind of saturation effect. The index decreases, but it kind of levels off at high organic nitrogen. And but when you go to higher morphological indices, it levels off at a lower level. Here's something you can learn from these models by graphical analysis, difficult to discover with neural networks, difficult to discover with certainly a linear model cannot even capture this kind of behavior. This is behavior that may be in your data, which you're not showing. All right. Well, what about accuracy? Well, in this paper, we compare the accuracy of NPR and neural networks. So both the R squared and the mean square error and the F statistic and the probability of the F statistic. So for example, that particular model I showed you, actually the neural network got a higher R squared. But we can compare, is that significantly higher? We can take the ratio of the F statistic and the ratio of their mean square regression gives you an F statistic. And we can calculate an associated probability. And it turns out they're not statistically significantly different from each other. So the NPR gives you as good a fit, and it gives you all these other advantages. You give in terms of utility, ability to analyze, ability to communicate, share. So someone else can take your model and use it and see how it works for their data set or their river, or just to see what is it telling you. Okay. Confidence interval. So this is work that I did for NASA in recycling nutrients in space from waste produced by the astronauts after they eat food. They produce human waste. We turn it back into nutrients. We feed it back to the plants and grow more food. So this is what they'd have to do for a Mars mission, because a 3-year mission would be tough to ship enough food along. So anyway. We were trying to predict photosynthesis rates based on various parameters. I'm not showing that here. What I'm just showing is the predicted values of the photosynthesis rate. And I've plotted them kind of sorted in order. So you can see the low photosynthetic productivity to high photosynthetic productivity. And a little faint in there, but you can see the green line in there, right? And the black dots are all the measured data points that were in our data set. These two black lines here are the prediction interval. So that's the calculated 95% confidence interval of the observations. And if we zoom in here and just look at closer in at the predictions, then we can see here, here's our prediction line again. This is the confidence interval. And you can see that it's the range for the confidence interval is much narrower than for the prediction interval, because it means because when you have a lot of data, you can make be much more confident about your prediction. So the range is very, very much shorter, okay, narrower. And so again, this is something straightforward to compute, relatively straightforward to compute this for a model like a multilinear regression model. Very complex to calculate something like this for artificial neural networks. Okay. Here's another case. I worked with Mike Lewandowski, the late Mike Lewandowski from Pace University. He collected many years of data. Every week he would walk out to the Hudson River in Manhattan, and he'd collect, and the East River, and he'd collect a water sample and bring it back to his lab. And he'd look at it under the microscope to see what phytoplankton were present, and he'd measure various water quality parameters that we see here, including hydrological parameters. And he wanted to see, could we predict what's going to be present based on these? Is there any dependence? Okay, so we did the fit, and we came up with the model for one of the phytoplankton species as a coded variable. All we did was the value of y is simply set as 1 for present and 0 for not present. So it's what we call a coded variable. And we could predict that by pH, DO, salinity, and salinity. The other things didn't matter too much. I have a feeling salinity might be a surrogate for tidal cycle, but anyway. But interesting thing that we could do, using the confidence interval approach, we could make a contour curve for the two most important parameters for R. setigera, one of the species of phytoplankton, and make a contour plot of when it was present or absent based on salinity and temperature. So the black dots here, the black diamonds, means it was absent. The open circles means it was present. And you can see there were high temperature cases where you get both presence and absence, but lower probability. We could calculate this dashed line here. It's kind of a dividing line where on average it's 50% probability of being present. And this solid line here means 75% line chance of being present. So that means that R. setigera is very likely to be present if at high salinity and low temperature. If you get to high temperature, then its probability drops down. Right? Something you can do with this kind of model. Finally, I want to give an example that's not biology, chemistry, physics. It's a business application, but it's still in the environmental field. This had to do with an industrial retail sales outlet that sold industrial supplies and equipment to industry, including to the water and wastewater industry. And they had asked me, they had about 60 retail outlets that they had measured about 30 different parameters for, and they wanted to be able to predict the profitability as measured by gross margin for those outlets. And it turned out that the significant variables were the ratio of supplies to equipment sold by a store turned out to be the most important parameter, but market share was the second most. And some other things were important as well. Interestingly, so here's the model, and you see that there's a linear term, and then a couple of inverse terms, another linear term. But I got a pretty good fit, 82%. And interesting thing was, if I did that kind of parametric curve and plotted the profitability versus market share at different ages, because you can see here market share and age interact with each other, you see something useful. You see that for average age, market share doesn't seem to matter. And for older stores, market share doesn't matter. But for new stores, stores that had low market share had lower gross margin. Okay. Does that mean that they should get rid of new stores, or they should just wait until the stores establish themselves? What this means to them is kind of up to them. But this is information difficult to capture by other means. All right. Also, of interest, I mentioned there were 13 things they had measured. There are a number of variables that turned out didn't contribute to the model at all. So tailor fit would simply not pull those in. All right. Going back to tailor fit, I just want to show you very quickly. Here's this model that I have. These are the predictions in this column here, and these are the errors, the residuals. I can very quickly plot these things. I mentioned things that you can do here. I can look at the histogram of the residuals, nice normal distribution. I can check the normal distribution by looking at the cumulative distribution, gives me that nice sigmoid shape. And I can download this graph. And I can look at the QQ plot. Perfect, very nice normal distribution. I can very quickly plot the residuals versus, this is simply in order, and I'm getting that randomness here, but I want to make sure it doesn't depend on something else, like does the residual depend on age? Not really. Does it depend on how much cement is in there? Right? These are checks that you want to do in your model, right? And I could say, okay, so let's see, what's going to be important? Cement is obviously, content is obviously going to be important. I can look at the importance ratio for cement, and it's added a column here for importance ratio. And let's see, compare the importance ratio of water And I like to look at the RMS value here, which is here. The importance ratio for cement is 0.58, for water 0.21. So I would say cement, that the strength is much more sensitive to cement content than to water content, according to this. And finally, the other thing I can do is I can go into the, I have to remind myself where this is, I can show my confidence intervals, and it creates a new column. And here's the confidence interval next to the residual. So my predicted value for example, this first row here, the strength was about 80. My predicted value was 58, plus or minus 2.6 is at a 95% confidence interval. Okay, so these are things, again, relatively easy to do if in regression context, and it's built into Taylor Fit, which is available to everybody. So that concludes my talk. There seems to be a lot of technical details here, and you have to know those technical details, but it takes some practice. Modeling is an art, as I said, as well as a science. So with that, I just thank you. And I also want to thank not only ABET, who sponsored this webinar, but the patrons of the Academy that you see here on the screen.
Thank you so much. We really appreciate it. Okay, we are going to open up for questions right now. If you have a question, you can type it in the left-hand side of your screen. It'll say attendee chat. You can type your question right there.
And Marisa, you're going to read any questions to me? Because I don't see them on my screen.
I don't see any yet. I can read them to you. Let's see. As soon as I see one, I can read. Okay, here we go. Do you see that?
No, I don't. If I stop the presentation.
Okay. Sure, that's fine. How long does it take to design a new model?
You saw me create a model for concrete. It took me minutes. And that's a common situation. Sometimes it'll get slow. It'll slow down if you have, let's say, thousands of rows in your data, and you start to get many terms. Then sometimes the program will churn for a couple minutes in between adding and removing terms. So in such cases, it might take you an hour. I like to say that computations are cheaper than data. You spend so much time collecting data, you can doing the calculations is not a big deal.
Okay. What's the link for the website? The model Excel file?
Okay, it's not an Excel file, so I can show it on my presentation again.
Okay.
I guess let me put presentation there. So you see it at the bottom left here, www.tailorfit-rsa.com. RSA stands for Response Surface Analysis. And when you go in, you can download a manual, a detailed manual, and you can upload your own data. And it's all done, calculations are done locally on your own machine.
Excellent, thank you. Okay, another question. I ran the Lydia Pinkham dataset in Taylor Fit. The series feature did not make a difference in the prediction. What am I doing wrong?
So Jerry, now I am able to see the things.
Okay, great.
I don't know what you did wrong. I'd have to look at it. I have run the Lydia Pinkham data, and one thing you have to do is you have to turn off the zero lag. So I didn't go into time series methodologies here, but I turn off the zero lag and I add lags 1, 2, and 3. So I can very quickly show. You still see my screen?
Yes, now we do.
Okay, so I'm going to clear the project. This is the start screen. And you see it has some built-in, two built-in data sets, the miles per gallon data set, and Lydia Pinkham is the one that he was talking about. And this is a time series data set. So you see these two rows here. This is year-by-year data of sales and advertising for this company. And what you have to do is add in lags. You want to use previous years as independent variables, and usually you want to turn off the 0. So now I'll recalculate, and I'll go in here, and I do have significant. This is advertising from 2 years ago is significant, and it looks like advertising from 1 year ago goes in, and after I add one, I had to take out the previous one. And I could still put in sales from 2 years ago seems to affect this year's. And again, now I have to go in and remove non-significant terms. So you go iteratively here, going back and forth a little bit here. But okay, so you get the idea. I hope that helps, Jerry.
Okay, do you see the next question, or do you need me to
can see it. Is it always a rule of thumb to plot predicted? I wouldn't call it a rule of thumb. It's a rule. So yes. There's a great book on regression, Draper and Smith, that explains the theory behind this. Okay. Adam Bell says, are there easy ways to tell if R squared is being abused in a peer research paper? Easy ways. You've heard of p-hacking, I suppose. Go look it up if you haven't. There's been a lot of controversy about this. Again, that's a big question. It depends on a lot of context. I don't think I want to address it right now. Maybe I will say it also depends on their history. What p-hacking shows is if everyone always comes up with right at that 5%, that's not likely to happen by chance, and that's an indication that if their studies always are at 5% probability, that they might have been squeezing things, sometimes unconsciously. Andy has asked me about the comment on the need to clean up data. Oh yeah, you have to do a lot of cleanup. You have to look for outliers, and the manual that you can download with the program has quite a bit of detail about this, and there are graphical tools within TaylorFit that help with this, although most of that has to be done outside of TaylorFit in your original spreadsheet program. Like missing data, for example, has to be removed. TaylorFit does not handle missing data. Okay, you're welcome. So if you're going to try TaylorFit and you have problems, reach out to me. I'm open to helping out, to answering questions. Sometimes, in some cases, I might even be willing to collaborate with doing studies if there'll be some useful outcome from this. So.
Excellent. Thank you so much. It looks like all the questions are answered, and like Dr. Vicari said, you can email him with any additional questions you might have.
Can I answer one more question here? I saw that Walter
Sure.
Is normality of data relevant? So that's an oversold thing that says that regression requires that the data be normally distributed. It's not exactly true. What it requires is that the residuals be normally distributed. And you saw I did test for that when I was done. Only after you're done modeling, and even if they're not normally distributed, your model is still pretty good. But the only problem that it comes is you still can have a good model, but the exact calculation of the probabilities involved is not accurate. That's what happens when you don't have a true normal distribution of the errors. So your data does not have to be normally distributed to begin with, but your residuals should be normally distributed for those probabilities to be meaningful. Okay.
Great. Thank you.
Okay. Yeah, we
Our
got
next,
one more.
one more?
No, that was it. We got
Oh,
one more
okay.
question. So let me
Okay.
put the presentation back on and get back to the slides.
Sure. And I just want to tell everyone that our next webinar will be on March 2nd. A few folks from Los Angeles County Sanitation Districts will join us to discuss their San Gabriel River watershed project, balancing water needs of the community and the environment. You can go to aaees.org and go to our event page to register. Just a reminder, if you're not yet a member of the Academy and you're considering joining, you can just email me to discuss your membership options. My email is mwaterman@aaees.org. And that wraps it up. We will have a recording of this event up on our website by tomorrow and possibly a PDF, I believe. And if you need any links or anything, you can always email me. Thank you so much and have a great day, everyone.
Bye.